Hi, I'm Ravi Chugh from the University of Chicago. What I'll be presenting today is work that my students and I are doing on trying to combine programming and direct manipulation. And so a running theme for this talk is going to be Ferris wheels. So here is a picture of the first Ferris wheel that was built in the 1890s, about 5 hours up the river from here. And so let's suppose that we want to make a presentation on the history of Ferris wheels. So what we'll want to do is to design a bunch of diagrams that help show how Ferris wheels work. So to start, let's imagine that we'll use a direct manipulation system like Illustrator or PowerPoint to make these diagrams. So to start, we would draw a circle for the wheel, we would draw a spoke along the circle, draw another spoke along the other edge, and now we'd start to draw circles and squares for the passenger cars, copying and pasting them and manually positioning them around the edges. Okay, so now we would copy and paste our spokes and our passenger cars a few more times, move them where they ought to be, and pretty quickly we get our first kind of iteration of our design. Okay, so now let's say we want to make a bigger version of the wheel. So if we grouped all of the elements and scaled them, we see that the passenger cars got really big too, which is not really what we want. So instead, we would probably have to scale the wheel first, reposition it back in the center, and move the passenger cars along the bigger wheel now. Okay, so now we've got our bigger wheel. Let's say we want to create a rotated version of it to show how the wheel rotates over time. So if we grouped all the elements and rotated them, now all of the passenger cars have kind of fallen over, which is not quite what we want. And so what we would probably have to do is ditch the passenger cars that we made, start from an initial perpendicular one, copy and paste it, and manually position it around the edges. Okay, so churning out different variations is starting to get tedious, especially if we wanted to change a design parameter such as the number of spokes where it's not a power of 2. Okay, so instead, those of us in this room might choose to use a programming language instead to generate these different diagrams. Right, so we would open our favorite text editor and pick our favorite language, and then we would need to start drawing shapes. But really, drawing in a programming language means going into the text buffer, typing some symbols, running it, and see what comes out. Okay, then we would go back to our program, add a couple more definitions, run the program, and see what comes out. Okay, so now that we have gotten basic things drawing, now we would think, how can I set up my program so that there's relationships that are captured in the output? Right, so now I would maybe go and add some relationships between the left edge of the line and the circle, run the program to make sure that they snap up correctly. Then I would go back into the program, add a relationship between the right side of the circle and the line, make sure they kind of line up appropriately, and continue to go back into our program, relating more shapes in our output. Okay, so now we've got a basic handle on how the program is working, so maybe now I can sit down and write a bunch of code to generate a whole bunch of shapes that are already kind of positioned where I want them. Okay, so now the design is starting to take shape. And so now we think this might be a good time to pause and group or refactor our program to write a single function that generates the design with all of the design parameters as arguments to our function. Okay, so now at this point, if we want to change any of the design parameters, we can go back to our function call and tweak those numbers, change them to different constants, run the program, and see what comes out. If it doesn't really line up with what we want, we would go back to the program, tweak some more numbers, and continue to kind of go back to the code, tweak numbers, run, until we get a configuration that we're happy with. Okay, and so at the end of this process, it's great because we do have a high-level reusable function, but remember that it took us like 42 steps to actually get here. Okay, and so early on in the design process, the program was really disconnected to what we were trying to do, and only later on did it start to become useful. Okay, on the other hand, direct manipulation allowed us to get off the ground really nicely and with intuitive feedback, but then when we wanted to do something complex, it became really tedious. So the goal is to ask whether we can combine the best of both programming and direct manipulation in the same system. So that is, we'd like to be able to start by directly drawing shapes in the canvas and have the system automatically generate a starter program for us. Then we would like to start declaring intended relationships in our output, again using direct manipulation, and have the system automatically refactor our program to match those changes. Then we would like to continue to directly manipulate the output, adding and grouping new shapes, and again have the system refactor our program to match our changes. And then we would like to be able to directly modify low-level design parameters directly in the output and have the program be updated in sync. Okay, so what we're after here is really to be able to build interactive programming systems where we can build programs with many fewer keystrokes. Okay, so as Brett Victor has described it, we'd like to do less blind manipulation of symbols, and instead we'd like to do more programming by directly manipulating output. So in this talk, what I'll present is a research prototype called Sketch and Sketch that we've been developing to try to start to achieve this goal for the particular domain of vector graphics. And so I'm going to spend most of the rest of the talk demoing the tool. And so to give kind of a high-level overview of what we're going to see, there's basically 3 parts of the demo. The first part of the demo is to show how Sketch and Sketch comes with a programming language that's just an ordinary functional programming language. There's not much special about it. You can write code, run it to produce output. And in the first part of the demo, we'll show how to write some text-based code that generates this radial array of lines. This will be the spokes for a Ferris wheel. Then in the second part of the demo, we're going to build a program that implements this geometric lambda pattern. And we're going to do this by starting from a blank canvas and iteratively building up the program using only direct manipulation. Then in the third part of the demo, we'll combine this geometric lambda logo and our spokes from before. And using both text editing and mostly direct manipulation, we'll implement this Ferris wheel of logos. Okay, and so the key takeaway is going to be that we're going to be able to build up a high-level reusable program with many fewer keystrokes than we would be able to if we were using a traditional programming language. Okay? Okay, so now let's head over to the application, which is just running as a web app in my browser. And the left half of the editor is a text box where we're going to write our program, and the right half is going to be where the output SVG is rendered. So the programming language inside Sketch and Sketch is a little functional language. It's got Lispy-like syntax, but it's not. It's just a really hand-rolled kind of small language. There's nothing special about it. Okay, and so we're going to start by just writing code to draw shapes on the output. So we can, for example, draw a gray line with width 4 from, let's say, the point 100, 100 to 200, 200. And run our program, and out pops our first little line. Okay, now let's say we wanted to define our line in a name, in a variable first. So we can define a new top-level definition to bind our line definition, and then refer to it in our little main expression here. Okay, so now let's take this myLine definition and turn it into a function that's parameterized over a couple of arguments. Okay, so what we'll do is we'll define a function, a lambda, that takes 2 arguments. I'll call them cx and cy for center x and center y. And instead of drawing this line always from the point 100, 100, let's draw it from the arguments cx and cy to 200, 200. Okay, so now I can go and call my line with a couple of different point arguments, and out should pop out 2 lines. Okay, so nothing so exciting so far. So one more thing that we'll do while kind of doing normal traditional text editing is to turn this function into one that not only draws a single line, but draws this radial array of lines. Okay, so we want this wheel of spokes. So to do this, what we'll need is to define a list of points that's going to define the endpoints around our wheel, our circle. And I'll start by just using the empty list just so that we can get the program set up. And so once we have this list of points, we're going to map each of the points, x, y, that's going to be around the edge of the circle. Oh, and now I've made my text size a little bit too big. We're going to map each of those points to a line that's drawn from the center point, cx, cy, to the point xy that's around the circle. Okay, and so once we have our list of points, we're going to map each of them to this line. And the next question is, how do we get this list of points? Right, so we've initialized points to a dummy list. We need to actually compute a list of points. So Sketch and Sketch comes with a library of just basic functional programming utility functions, and also some useful SVG manipulating functions. So I'm going to tab over to a window where I have this prelude file open and show you a function that's going to help with our task here. Endpoints on circle is going to take a center argument, the number of points, rotation, radius, and it's going to compute a list of points for us. Okay, so what we need is to call this library function inside our spokes function. Okay, so endpoints on circle, notice, takes a bunch of arguments. We have center x and center y. We have those already as arguments to spokes. But we also need the number of points, the rotation, and the radius. Okay, so I'll add those as parameters to my function. Make sure I've got enough parentheses. And now we can call our spokes function with, let's say, center 100, 100. Let's draw 7 spokes, maybe with radius 60. We'll not rotate our wheel. And so if we've typed everything correctly, out pops our wheel of lines. Okay, so everything so far has been completely traditional text-based programming. In the next part of the demo, let's start implementing this geometric lambda design. Okay, and so unlike using a traditional language where we would have to start by typing code to generate shapes, this time we're going to start using the built-in drawing tools to directly draw shapes in the canvas. Okay, so we'll start by drawing a rectangle. And notice how Sketch and Sketch has auto-generated a new definition in our program. And notice how the white space and variable names are chosen to be readable so that if and when we need to dive into the code, we kind of have a sense of what's going on. Okay, and so just like a normal language, if we wanted to, let's say, make the rectangle wider, we could change a number and rerun it. But better yet, Sketch and Sketch allows us to directly manipulate shapes in the output while it updates the constants in our program to match. Okay, so we can change basic attributes like the position, the x and y, as well as width and height, and other attributes like the color of the interior, the fill of the box, as well as stroke parameters. Okay, and so while I'm making each of these changes, Sketch and Sketch is updating our program in sync and re-rendering the results of the program to give us this kind of live feedback. Okay, so remember, we want to draw this kind of lambda logo, so we need a couple more shapes, we need a couple more lines. So I'll continue to use the drawing tools to draw shapes in the output, and again, Sketch and Sketch is adding new shape definitions that are completely unrelated to one another. They all have just separate constants as their design parameters. Okay, so we can start to fudge our lines a little bit to try to make it more like a lambda, but really what we want is we want the endpoints to really kind of snap up exactly. Right? So how would we do this in a traditional text-based language? So first we would say, okay, what are the numbers that define the position of this box? Well, that's 73 and 228. What are the numbers in the program that define the endpoint of this line? That's 88 and 248. So what we would do with kind of normal text refactoring is we would do something like pull these numbers up into new variables. Let's call them top left x and top left y. And now, in place of those constant literals before, we would use our new variables. Okay, so by using top left x and top left y for both points, now the points should be snapped together, which is the relationship that we wanted. Okay, so that's normal text-based refactoring. Instead, Sketch and Sketch provides automated support for introducing equality relationships like this. Okay, so I'm going to undo this manual text editing that I just did, and instead go back to this kind of having 3 shape definitions that are completely unrelated. And instead, what we'll do this time is we will select those 2 points that we're interested in, and press this button that's labeled A equals B to instruct Sketch and Sketch to try to refactor the program to make these values equal. Okay, and so when I press this button, Sketch and Sketch is going to automate that text-based refactoring that we just did manually. Okay, so when we make these 2 values equal, Sketch and Sketch has added 2 new variables to the program here. And notice how the auto-generated names indicate where these numbers came from. So they both came from the rect1 definition, and furthermore, they came from local variables x and y. Okay, and so now these variables are used in both shape definitions, and so when we directly manipulate any one of the objects in the output, the other object is affected as well, because they're both defined by the same constants in the program. Okay, so in this way, we can continue to select the pairs of points that we're interested in and instruct Sketch and Sketch to introduce variables to make them equal. So we need one more pair of clicks here. And so now at this point, and it keeps getting rid of my white space, bummer. So at this point, notice how we've got variables for the top left corner of our rectangle, the width and the height, and the positions of all the other shapes are computed in terms of those design parameters. Okay, so that's it for the basic geometric constraints. Next, let's see how to get the color and the stroke width of the different lines to match up. So just like we could select positional attributes in the output, we can also select color attributes as well. So we can select the stroke sliders for each of our 3 shapes, and again, instruct Sketch and Sketch to make them equal. And in response, we get a new stroke variable that's been pulled outside the definitions, initialized to one of the 3 color values chosen arbitrarily. And this variable is now used to control the color of each of these 3 lines. Okay, and so by changing any one of the colors, the other 2 colors are affected as well. And similarly, we can select the stroke width sliders, instruct Sketch and Sketch to make them equal, and so now we have a stroke width variable that again is used to control the widths of all 3 of these lines. Okay, so one more relationship that we might want to impose on this logo is that it always remains square when we scale it. And so to do that, we can use the width and height selection lines on our rectangle, make them equal, and Sketch and Sketch has chosen to use the width value now both as the width and the height of our rectangle. Okay, so now whenever we scale the shape in one direction, the other dimension is changed as well. Okay, so we've gone from having no shapes to having a program with all these relationships kind of encoded, but all of these shapes and their kind of design parameters are defined as top-level definitions in our program. Next, we want to start refactoring the program to turn it into a single reusable function that we can then use to generate many different variations of the logo. So Sketch and Sketch provides several tools for helping with this kind of grouping and abstraction process. So one of these tools allows us to select a point in the output and several shapes that we want to group around that point. Okay, so when I click the group button, Sketch is going to look for all the definitions that contribute to the selected shapes and turn them into a single top-level definition that generates all of those shapes. Okay, so notice how when we press group, Sketch and Sketch has collected all of those definitions inside a new group definition, and so now this one definition draws all 3 of the shapes that we had before. Okay, but the design parameters are still hard-coded constants inside this definition. So to turn this into a function that's parameterized over the design parameters, we can select our logo and hit the abstract button to turn a new group into a function that's parameterized over these design parameters. Okay, and so notice here how it takes. No crashing yet, good. Okay, good, so we've got a bunch of these design parameters and the anchor position to draw the shape. And so now our single logo is a call to the new group function with this anchor argument 103. Sorry, this is kind of like a reverse application. There's really nothing special here. Call this group function with all of these arguments and then this point. Okay, and so directly manipulating this call is just changing the arguments to that function. And so now if we want to copy and paste or duplicate, what that means is just add a new function call to the same function. Okay, and so because each of the design parameters are different constant literals, we can change them independently at call sites without affecting the other shape. Right, so all of the kind of geometric relationships were encoded inside the function body, and all the design parameters are per function call. Okay, so what we've done is we've gone from drawing shapes to relating shapes up to building a reusable abstraction. Next, in the third and final part of the demo, let's put together this logo function that we have with our wheel of spokes to make a Ferris wheel of lambdas. Okay, so that's something you hear every day, right? So let's get rid of the second logo. We don't need it. We're just going to use one version of it. And so Sketch and Sketch provides a couple of tools for basic patterns of repetition. So we can select our Lambda logo and press the repeat around button. And in response, Sketch and Sketch has inserted a call to a library function called radial array, which takes several arguments. So the first argument is the number of shapes in this array. And there's a couple of annotations here. So this exclamation point freezes the number in the program, which tells Sketch and Sketch not to change this number when the user directly manipulates any shape. Instead, this second annotation, 1 to 20, says that this value ought to be in the range 1 to 20. And furthermore, the editor draws a slider at the bottom of the canvas that allows that number to be changed using direct manipulation of this slider. The second argument here is the radius of the wheel, and Sketch has drawn this little helper widget to easily change the radius. And the third argument here is the rotation, which again comes with a slider that we can use to tilt the wheel left and right. Okay, and so maybe I'll make the logo a little bit smaller so that we can fit more of them around the wheel. Okay, good. So one thing that you might have noticed now is that the lambdas actually aren't quite centered around the center, right? And that's because our new group function was parameterized over a top left anchor and not the center of the logo. Okay, so we need to kind of like translate the anchor point to this logo function, but no problem. This is a general purpose language, so we can edit the code to write a little wrapper around our new group function. Okay, so remember that what new group is a function that takes a bunch of colors and things, and then the position to draw the top left corner of the logo. And so what radial array is doing is internally it's computing a bunch of points around a circle and then calling our logo function with each of those points. Right? So to make that explicit, really what is going on is for each point x, y around our logo, radial array is calling new group with that particular point. Okay, so I've just kind of added a lambda expression here to make that explicit. But what that means is that if we want to call our logo function with a different argument, if we want to translate it, this is our opportunity. This is the chance where we can, translate it a little bit before calling the function. So to kind of make sure that will work, let's just start by translating each anchor point by a couple of hard-coded constants just to make sure that we've identified the right piece of code. Okay, good. So now all the anchors have kind of shifted up and to the left a bit. But really what we want is to get the anchor to be exactly in the center of the logo. Right? So we want to translate the coordinates by half of the size of the logo. Okay, so what is the size of the logo? So remember that there was this rect1w parameter, the width or the size parameter. So what we need is we need a name for our size argument, 45. So right now it's a constant literal. So what I'll do is I'm going to add a new local variable called size, initialize it or bind 42 to it. And so now we have a name for the size parameter. And so instead of offsetting our anchor by random constant literals, we can offset them by size divided by 2. Okay, and so if we've done our math correctly, now we have basically translated the anchor so that it'll be in the center, and then we call our logo function with that anchor. Okay, good. So let's see. We've got our array of lambdas. We've got our spokes. We also wanted, remember, we also wanted kind of a central circle in the middle of our Ferris wheel. So next, let's add a circle that's going to form the kind of main hubcap of our wheel. Oh, good. And it's kind of automatically randomly picked a metallic color for me, but we can, of course, change it if we need to. Okay, good. So we want the center of this circle to be exactly equal to the center of our wheel of logos, and we want that to be exactly equal to the center of our spokes array. Okay, so we can use our trusty friend makeEqual to introduce new variables in our program, which have very helpful names, K4759. And just like before, these variables are used to now control the centers of each of those three previously unrelated expressions. Okay, so we're getting close. But now we're at the point where the way that we control the number of logos is unrelated to the way that we control the spokes. And so we need to kind of we need to introduce those relationships. So one way that we can do that, one kind of little fun way to do this is, well, we've got these slider annotations that we can add. So why don't we add slider annotations for these other parameters as well, for number of spokes, the radius of the spoke, or the length of the spokes, the rotation of our spokes. And so now we'll get a whole bunch of sliders in the output, where we can change the number of spokes. Sorry, this is the number of logos. This is the number of spokes. We want them to always be equal. So just like we could select color sliders, we can select these helper sliders at the bottom, tell Sketch and Sketch to make them equal. And so now we have a single variable in the program that's going to be controlling both. Ooh, what did I do here? Are they changing? Oh man, what did I do? Maybe I selected the wrong slider. Let's see if we can debug this. Undo, undo. So let's see, this is the number. Oh, okay, great, excellent. This is good. So this is a live demo. This is nothing fancy going on here. So I told Sketch and Sketch to make 12 and, let me get rid of this. I told Sketch and Sketch to make 5 and 12 equal. What it tried to do was say, okay, you're trying to make the number 5 equal to the number 12, but actually this number 12 is frozen, so Sketch and Sketch is not allowed to touch that number. So that's why it didn't replace this constant with the variable that it inserted. So right now I need to unfreeze that number so that when I tell Sketch and Sketch to introduce a variable, it then has permission to do so. Okay, and so let's see, while we're at it, let's just add a slider for the radius too. So now if we select both of these sliders for the spokes and the number of cars, press make equal. Okay, now you can clap instead. Okay, good. Okay, good. Sorry, I'm ready. Yeah. Okay, good. So thank you. What we can do is now we'll make the two separate rotation parameters equal. We'll make the two radius parameters equal. And so now we've kind of locked up all of the arguments for each of the arrays of spokes and the logos. And so now we can tweak all the kind of high-level design parameters that we wanted to, either directly manipulating shapes or directly manipulating sliders. And then when we're done with all this, right, we can turn off these helper objects. We can export our output to some other SVG editor. And maybe we can even take this high-level program and reuse it somewhere else. Like, for example, if we wanted to generate a whole bunch of Ferris wheel diagrams for a presentation, for example. Not that I did that. I use PowerPoint, but hopefully one day, future work, we'll get to this in a few minutes. OK, good. So now let's pop back over to the slides. So we've seen a lot in the demo. We started with kind of a normal text-based programming language. We did a little bit of typing, but then we did a lot of transformations with a lot of automated or semi-automated support from the system. Right? And so in particular, Sketch and Sketch allowed us to directly manipulate at various phases in the design process. And Sketch and Sketch came with refactorings that were kind of tailored to each of these developments of programming in this domain of SVG. And we were able to basically build up this kind of high-level program with many fewer keystrokes, I think, than you would if you were using a normal kind of programming language. And so specifically, if we had been using a programming language from the year 2015, for example, instead of having to start by writing function calls in our program and running them, we were often able to just draw shapes in the canvas. Right? Then instead of always having to introduce new variables into our program to add new relationship constraints, we were often able to select things in the output and tell Sketch and Sketch to make them equal. Then instead of having to manually refactor and group and abstract our definitions, we were able to select shapes in the output and again have Sketch and Sketch group and abstract them for us. And finally, instead of having to look through our program and kind of hunting and pecking for the constants to change, we were able to awfully just directly manipulate design parameters in the output. Okay, and so while this kind of workflow significantly reduces the amount of manual text-based editing, there's still a long way to go to really kind of achieve a much more seamless combination of programming and direct manipulation. So next, I want to point out a few of the many limitations that the current system has, which lend themselves to natural areas for future work. So in our demo, we saw many cases where Sketch and Sketch could introduce a variable to relate to expressions. In more complicated cases, Sketch and Sketch sometimes inserts a really kind of complicated, very verbose arithmetic expression that is mathematically correct, but is not something that you would write by hand. And so in the future, we plan to incorporate a smarter algebraic constraint solver that can simplify these expressions much more effectively before inserting them into the program. Another kind of limitation is that currently our refactorings for grouping and abstraction require that the program be in the form of a bunch of top-level definitions followed by main. And then the user can select certain top-level definitions by direct manipulation to trigger the refactoring. But in the future, we would like to provide the similar kinds of refactorings, but for programs in more arbitrary structure. Another limitation is that currently the way that we decide what constants to change and solve for while we're dragging the shapes is relatively naive. It's very naive. And so sometimes you get situations where maybe you try dragging a shape to the left, and instead it grows to the right. And so again, by incorporating a more general algebraic constraint solver, we expect to be able to provide more intuitive live interactions for more cases. And then finally, for all of these kinds of refactorings, there's many different programs that we could have produced. And so currently, our approach is to use various heuristics to automatically choose one of the options so that we give the user some immediate feedback. But on the other hand, that often means that the user doesn't really get the program update that they expect. And so in the future, we plan to include the user in the loop when there's lots of ambiguity to better resolve what the user actually intends. OK, so stepping up a level, so the approach that we've taken here is to start with a completely traditional vanilla functional language and add direct manipulation capabilities to it, instead of starting with a direct manipulation system and trying to make it more programmable. And so we've chosen this approach for a couple of reasons. The first is that we hope that by starting with a general purpose language, that we can reuse a bunch of this effort when we think about other application domains. Another reason is that no matter how many built-in tools come with a direct manipulation system, there's always going to be limits to what the tool can do well automatically. And so by using a general purpose program as the representation, we enable expert users and library writers to customize features beyond those that are provided. So the transformations that I showed, some of them are actually general. They're independent of the domain. So the way that we relate and abstract values doesn't take into account anything about SVG. But other transformations, like for drawing and grouping, are domain specific. And so our hope is that in future work, as we try to build similar kinds of workflows for other domains, like web application development, for document generation, for visualization, spreadsheets, and so on, we hope that there's kind of a class of general transformation techniques that apply broadly, but that each domain will require a custom user interface that's really catered to the programming idioms in that domain. Furthermore, let me go back a slide. So furthermore, the kind of language inside Sketch and Sketch right now is kind of a toy little language. But ideally, we'd like to be able to provide similar kinds of refactorings for your favorite real language, like Racket or JavaScript or Elm or whatever it is. Maybe the knitting language that we saw earlier. OK, great. So this goal of combining programming and direct manipulation, particularly for the domain of SVG, has been sought by many projects over the years. One area of related work can be described as dynamic drawing tools, tools such as Brett Victor's systems, as well as systems like Apparatus and others, which tend to take the approach of starting with a direct manipulation system and trying to make them more programmable. And in particular, they often try to limit or even prohibit the amount of kind of text-based editing that one can do. And so in contrast, we've chosen to start with a general language, again, because of the potential for reuse and extensibility. Another related line of attack are constraint-oriented programming systems like Sketchpad, ThingLab, and others, which allow users to declare constraints either on the program or on the output. And these systems lead to a similar kind of interaction that we're seeking. But in contrast, we limit all use of constraints and constraint solving to the program transformation phase. And so after that transformation, we have a normal vanilla deterministic program. That is, we don't have constraint solving in the semantics of our programming language itself. And finally, what we're trying to build here is definitely an instance of live programming where you want to see the effects of changes immediately, including more recent live programming languages by Sean McDermott, which are also trying to get this kind of backwards connection as well. OK, so to wrap up, the kind of high-level takeaway here is that we want to be able to build programs by typing less and directly manipulating more. And so Sketch and Sketch is kind of a first attempt to make progress in this direction by providing automated refactoring tools for this particular domain of vector graphics. And so if you'd like to learn more, our project page has our web app demo. It's got our open source implementation, which we built in Elm, which turned out to be a really great choice for us, and we're going to continue to really enjoy that kind of development workflow. We also have a bunch of videos that have more examples, as well as papers that explain the technical details that are under the hood. Thanks a lot. So I think there are 4 minutes standing in the way between us and Saturday snack. So if there's questions, I'm happy to take some.
Are you a magician?
No.
There are other examples of projects where you can convert from code to visual representation back. Like what you see is what you get editors on the web, but they always mess up your code. So if you write code by hand, then go to
Right.
it's messed up.
Right.
How do you avoid this?
So the question was, for those of you who didn't hear, am I a magician? The answer is no. So no, there's lots of these tools that do try to like auto-generate code and things like that. So no, there's a lot of other tools that, particularly in kind of areas described as program synthesis or program repair, that take a program and maybe a specification of what you want to change in the output, and they try to fit a new expression that fits back into your program in a nice way. But for kind of a more general kind of like programming domain, one where you really do care about the readability, the concrete syntax of your program, and the kind of visual output, I haven't seen anything like this yet. But for kind of general programming, like sorting lists and things like that, there are program synthesis techniques that really can take examples of what you want and come up with correct implementations of what you're after. We haven't, but so the question was, have we tried something similar for graphics or 3D modeling CAD tools? We haven't yet, but that is definitely one of the many kind of applications that stack up here. Yeah, I would love to be able to strive for similar kind of workflows in many domains where there is a good amount of kind of visual, inherent visual representations of what you're manipulating, and a lot of times it would be great to go backwards. If there are resources or people that would like to join the project, please let me know. We'd be happy to. Maybe who's standing in the center?
Yeah, so quick question. You mentioned connecting this to more languages. Have you considered connecting it to more mature drawing programs such as Inkscape?
Right, so that's a good question. So the question was, instead of extending general purpose languages with direct manipulation, have we thought about starting with Inkscape or something like that and adding programmability? Again, that's something that we would love to do. I think early, before I started working on this a few years ago, I think I was thinking, oh, maybe we'll build like a PowerPoint plugin to kind of do this thing. But so far, I think starting with kind of a clean slate editor was the best way to make progress on the underlying technology. And then once it starts to work better, then I think it makes sense to put in the effort of trying to make a plugin for a real system. But Inkscape would be obviously a great place to kind of deploy this work. In the blue shirt. So we haven't gotten there yet because we've been actually trying to make like the simplest choices at each place where there's a big design space and there's lots of knobs to turn. We keep kind of like turning it down to like the simplest setting, and it seems to be, we're not running into any walls yet. Like for example, in the way that we solve for new numbers when you're dragging things in the output, we're actually being very optimistic. We're not guaranteeing that when we compute a new update, that your program will even take the same control flow it did before. Okay, so we're actually optimistically assuming that the way that the program computed this number is going to be the same, even if we change other values in the program. And it turns out that for at least simple examples, when you've got high-level design, you've got design parameters that don't affect the way the program runs, that's a perfectly fine assumption. But in more general cases, we're certainly going to have to reason about control flow and function boundaries much more. But so far, we haven't tried to solve that, which might be a bigger bottleneck. Maybe one more question and then Saturday snack.
Whenever you export to SVG, do you preserve enough information so that, say, I want to do a CSS transition or animation of some sort, I could easily do that and the variables within it be like rotation?
So I think so. So the raw SVG that I showed really is raw SVG. There's no extra metadata. But just before that step, each number in the output is tagged with some metadata about the program evaluation that produced it. And so that's actually the hook that we use. When we change a number in the output, we say, OK, what's the metadata that came with this number? That gives us a bunch of possible things we could change in the program. And then we choose an update based on that. And so we definitely can apply a similar kind of tracing and provenance strategy for HTML apps where you have CSS that you might want to tweak and things like that. OK, cool. Thanks a lot. I'm happy to chat more in the break.